And start recording, please. So this is Xian. Xian is a reference point in my life. He's one of my best friends. He's one of the most wonderful human beings I know. And besides that, he is an expert on a few things that I don't know anything about. And he's going to talk about, I think, different sources of gravitational waves. I might learn something from him. He used to be my postdoc, but this is the usual situation in which the student clearly superated the professor in all aspects. So go ahead, Xian.
Okay, Paul, you're being too modest. Hello, everyone. This is Xian. I might switch off my video soon just to save some bandwidth. So again, hello people from Cuba.
We want to see you.
Greetings from China. Okay, people are leaving messages in the chat box. Okay, let me switch. Okay. So today I'd like to talk about gravitational wave sources.
But Xian, sorry, can you really insist that you switch on your camera unless there is a big problem for you? Because
no,
otherwise it's going to be very boring.
Sorry, Xian. Just one thing. I see that in the chat somebody is asking what time do we start today, and they are from Cuba. I'm just not sure if everybody is like, maybe Pau can just check it if somebody is unable to connect.
I see.
No. I think this is fine. Laurel, right? They know because they got an email.
Okay.
Yeah, they got an email. If he's connected, he will know that he's already connected.
Yeah. So go ahead.
Okay. Sorry. Okay. Sorry.
Yeah. So, like I said in the beginning, I didn't prepare much. I did thought about several questions I think might be interesting to discuss here. So I assume people here already know what a gravitational wave roughly is. So I will start by saying that yesterday we have detected gravitational waves, okay, by LIGO and Virgo. But if you have been following the news or if you are studying the papers recently, you see a lot of papers about black holes, big black holes, small black holes, how they form. But have you thought about the question, what we detect is a gravitational wave, it's a wave. How come we know these waves are produced by black holes? I'm not sure if you have a thought about this.
Have you people? This is an interacting. So far we have had a lot of slides and so on, but this is actually more the kind of talk that I like. So Xian is asking questions, and it would be nice if you.
It would be nice if you provide me some feedback, even if it is just simply no, I don't know. Just let me know that you are following, or if you have a great idea about how you can derive from gravitational wave it is a black hole, just let me know. Because to me, at the beginning, it was not very obvious.
Otherwise, I can just ask randomly. Diana, what do you think about this?
By the way, let me share with my screen if there's an option here.
Diana's hiding. Diana.
Hello, I'm here.
Yes. What do you think about the question that Xian asked?
Could you repeat the answer?
Yes, can you repeat the question, Xian?
Okay, we detected gravitational waves. Nobody can deny that. But just from this signal, how can we know it is from black holes? A wave can be produced by, a lot of other things, right? It can be, say, white dwarfs orbiting each other can produce waves, neutron stars, or even like an irregular neutron star rotating along its axis is also producing gravitational waves. A lot of things in the universe are producing gravitational waves. LIGO Virgo detected gravitational waves, but how come we know it must come from black holes, not other things?
maybe it can be determined by its intensity, knowing approximately what is the intensity of the gravitational wave that comes from a black hole. I don't know if there is some data about it, but I think it's a good method.
Yes, good. At least intensity, like the or in the more exact and the amplitude of gravitational waves, you might guess, oh, it's strong. It must be from something very intense. Could be a black hole, right? But actually, it's not. You can put a gravitational wave source, even if a very small gravitational wave source, or not black hole source, okay, very very close, and it will give you high intensity. Or if it's a black hole, you can put it very very far away in the universe. Then the intensity would be very very low. So according to your criterion, this low intensity source would not be black hole, but actually it is produced by black holes. So intensity is not the way we judge if or not it is black hole. There must be something else.
Oh, okay.
Any other idea?
I think
Hold on.
I want to speak.
Just go ahead.
Just
Just interrupt Xian. Just
yes,
talk.
please. Holland, you want to talk? You have to unmute yourself first.
Honestly, I don't know the answer. I'm just thinking.
Yes,
That's good.
just to think. What's your thing?
So,
But that's good.
What do you think?
If you knew the answer, it would be strange.
before, I'm just thinking about we can assume, we can calculate the mass of the source, but you just mentioned that it's not the evidence.
No.
So I'm just
what I said is, it's not the amplitude.
not the amplitude.
It's not the amplitude, but when you say mass, how it's a wave signal. I can draw a wave signal here. Sorry, I can use my hand. A wave. How can you know from this wave signal the mass?
I don't know, but I think there is a way I can calculate the mass.
Okay, so think about a wave. It's a gravitational wave, right? Wave has, besides amplitude, it also has a frequency. Some things oscillate fast, some things oscillate slower, right? So actually, the mass or what the object is encoded in the frequency. A good way to imagine this is that imagine two stars. These could be two main sequence stars or could be black hole neutron stars. They are on a circular orbit. Okay, if they are far away, they rotate very slowly. Now this is producing gravitational waves, but it will produce very, very low frequency gravitational waves, right? As the two stars lose energy because of radiation of gravitation and they get closer, it starts to rotate faster and faster and faster. So you see the frequency is increasing, but there must be a limit to the frequency. It cannot grow to infinity because in the end you are thinking about two astrophysical objects which has sizes. When the two things start to touch each other, then complicated things happen, and then this is basically imposing upper limit to the frequency you will see. Okay, if it's if these are two main sequence stars are very very big. For example, our sun is like 100,000. Actually, is 6 times 100,000 kilometers. Okay, it's very large. Because they are large, so when the two stars touch, the frequency is still relatively low because the stars are large, so they are not very close when the two stars already merge. So by this kind of thinking, you will see that stars merging will not produce very high frequencies. Okay, I think in fact when the stars start to touch, the frequency I think at most maybe well, if you talk about period, it's about the hours. Okay, the period is probably hours. Hours translate into frequency is 10 to minus 4 hertz. So LIGO Virgo is detecting gravitational wave in 100 hertz. So you immediately know these sources cannot be stars. Okay. Then we can try other things. Okay, we want the two objects to get closer, so the frequency is higher. So the frequency will fall into the LIGO Virgo, right? Then what objects are more compact than main sequence stars, than our sun? Well, we can think white dwarfs are pretty compact. They are very small. So they can get closer. And then when they get closer, their orbital frequency is much higher. But if you happen to know a little bit astronomy and know the sizes of white dwarfs, they are about the size of the Earth. Okay. Their size is also is imposing an upper limit to the frequency. The frequency is also very, very low, actually. The frequency is, if I didn't remember it wrong, it's about also 10 to minus 2, probably, 0.01 hertz, around that. Still, white dwarf merger will not produce 10 hertz, 100 hertz gravitational waves. So they are not LIGO Virgo sources. Then you have to try something even more compact, like neutron stars. A neutron star with one solar mass is of the size of maybe 10 kilometers. So it's much smaller than a white dwarf. So neutron stars are already like two very small points, and they get really close. So the frequency can be even higher. Then in this case, a neutron star actually can go up to actually kilohertz. Okay. So when they merge, you should see some frequency go up, and in the end, the highest frequency you see if these things merge in a neutron star should be kilohertz. Again, this is not what we see in LIGO Virgo. The frequency turns out to be too high. What we see in LIGO Virgo is a wave. The frequency goes up because the orbit is decaying, but it abruptly ended at around, say, 100 or between 10 and 100 hertz. Okay. So just simply from this fact, the upper limit of the frequency, we know they are not the stars, main sequence stars merging. They are not white dwarfs merging. They are not neutron stars merging. They're actually black holes merging. Black holes also have sizes. A 10 solar mass black hole has a size of about 3 kilometers. Okay, 30 solar mass black hole has a size of 100 kilometers. Okay, if you put these sizes, take these sizes into account and ask what is the highest frequency two black holes can get to, it's around the 10-100 hertz. Okay, so if I have explained this clearly, I'm not sure, but you will see that it is really the upper limit of the frequency that is telling us that these are black holes merging, not other things. Is it clear?
People, is it clear? Rainer, Solne, Jose.
Hi, can I ask a question?
Yes, please.
Of course.
Yes, what you said is clear, but how can we calculate the frequency of this merge depending on the mass of the object? Is that coming from Einstein's equation or is something else?
It's a very good question. Paul, you want to say something? I hear you.
No, sorry, it's because Sultan is trying to join, but he has the wrong link. Go ahead.
Okay. Okay. So in theory, how can we calculate the frequency? You might think, oh, everything is a very relativistic. It's GR. So our usual concept of the Newtonian the dynamics doesn't apply. Actually, it's not so correct, because most of the time, when the two black holes are, say, relatively far away, black hole has a size of Schwarzschild radius, okay? But when they are 10 Schwarzschild radius away, or even 100 times Schwarzschild radius away, their gravity on each other is relatively weak. And believe it or not, like Keplerian orbit describes the orbit very, very well. So you can use still the Newtonian physics to have a rough estimation of the frequency. When in Newtonian physics, the frequency is a distance cubic divided by m, and take the square root of it. So you can still use this classic equation to predict the frequency. I think only in the last few orbits, when the two black holes are already, say, 3 Schwarzschild radius away, 2 Schwarzschild radius away, does this Newtonian frequency break down. Otherwise, it's still very accurate.
Okay, got it.
Mm-hmm. Okay, if there's no more question, then let me just proceed by saying that so we know we are using this upper limit of the frequency to to interpret what kind of objects are merging, right? For black holes, because black hole has a size of Schwarzschild radius, so you can use the Schwarzschild radius and the orbit around it to basically predict what is the highest frequency you can get to if black holes are merging. So if you do the math a little bit and calculate, okay, I put the orbit around, let's say the Schwarzschild radius. Okay, it's already very unrealistic, but you use a Keplerian equation and get a rough estimation of the frequency. If you do that on a piece of paper, and you will see that in the end, the final frequency, the frequency when the two black holes merge, is proportional to 1 divided by the mass of the black hole. In other words, if black holes are small, the merging, during the merger, the frequency can get very, very high. If the black holes are very large, then the frequency becomes very, very low. Okay. Then this actually answers my next question. Yes, there's a question there?
Yes, if I can ask you exactly related to that, how can we intuitively see this relation? Does it stem from a basic equation from black holes?
Yes. Okay. Frequency is r. Let's say the distance of the two black holes is r. Okay, r cubic divided by m, and take square root of it, right? R, the smallest r you can get is m. It's proportional to the gravitational or Schwarzschild radius. The radius is proportional to the mass of the star. So this is a m to the cubic on the numerator, and you divide it by m, so you have a m squared, and take square root of it. It's m, so it's frequency. Okay, the orbital period actually. Sorry, I actually made it. What I was calculating was the orbital period. Okay, the frequency is the reverse of it. So you will see the frequency actually scales 1 divided by m. Okay, then if you have this formula in your head, then you can already try to answer this question when people ask it a lot, actually. So they say, oh, LIGO Virgo already detected a gravitational wave. Why we need another gravitational wave detector like LISA operating in space? Right? Has anybody here have not known LISA? What LISA is? I think maybe in the previous days the speakers have already touched upon.
No, they didn't.
No? No. Okay. So LISA is a space detector. Basically, you in a certain way you enlarge the LIGO Virgo to blow it with into an arm length, not 3 or 4 kilometers, okay, but 3 million kilometers. So you cannot put it on the Earth. So they have to launch it into space and form a triangle, a constellation. And you have 3 satellites forming the 3 tips of this triangle, and they are measuring distances mutually. By monitoring the distance change, you also detect a gravitational wave. Okay, this is another type. This is still an interferometer, but a much larger one. Okay, so this is what European people and plus the North Americans, basically NASA and ESA, are trying to do jointly. And the plan is we launch it around the 2035, maybe in 15 years. Okay, the technology is very, very impressive. Imagine you have one arm, each arm spanning 3 million kilometers, but they have to measure a very, very small change of distance because gravitational wave is very, very weak. How small distance they have to measure? it's about 1 picometer, 10 to the minus 11 meters. Okay, you have an arm of 3 times 10 to the 11. 10 to million kilometer, right? So it's 10 to the 9. Okay, 3 times 10 to the 9 meters to measure a small distance change of 10 to the minus 11 meters. Okay, so you have like almost 20 orders of magnitude to go over. Okay, but by that precision, you can measure another type of also gravitational wave, but really in a completely different frequency band. So obviously this takes a lot of money, billions of euros. Then people always ask, okay, LIGO Virgo has already detected gravitational. Why you have to launch such expensive detector, LISA? It's called a laser interferometer space antenna into space. Why are you wasting your money to detect something you already have detected? Anybody have an idea? So, or anybody see the point of launching this antenna? Yes.
Yes.
Mm-hmm.
Yes. Perhaps it's to get a wider frequency range to detect something.
No. In terms of frequency, both LISA and the ground-based LIGO Virgo are quite narrow. LIGO Virgo is centered around 10 to maybe 100 hertz. Way out of this region, the sensitivity is very, very, very poor. LISA is centered, is aimed at detecting millihertz gravitational 10 to minus 3. Okay, if you are way above or below this frequency, the sensitivity is also very poor. So in terms of bandwidth, the width of the band that you are sensitive to, LISA is not much better than LIGO Virgo. So it's not a bandwidth. Then what else?
Precision, maybe?
Precision. LIGO Virgo can already detect a gravitational wave amplitude of 10 to minus 20, 21. LISA, just like the length and the distance they want to measure, I showed you, is also measuring a gravitational wave amplitude of maybe 10 to the minus 20, 21. So in terms of the amplitude of gravitational wave they are trying to measure, they're more or less the same. Okay, it's not like LISA is measuring much weaker gravitational wave. No, not like that. So it's not a precision either in this sense.
Okay, Cuba people, Solnay, the salon at the Instec.
Maybe it could be because of in order to avoid, I don't know if that's possible, the gravitational field of Earth modeling the signal, something like that.
Very good. So the reason we have to launch this detector into space to detect the millihertz gravitational wave is because of what you said. On the Earth, millihertz gravitational wave will be swamped by the gravity from the Earth. Okay, the Earth is vibrating. We have earthquakes all the time, for example, and they are producing gravity gradients. We don't call them gravitational waves because these things do not propagate to infinity, but it's a gradient of gravity, and it will completely dominate the frequency band below, say, 1 hertz. So on the Earth, there's actually no hope to detect millihertz gravitational wave because your noise from the Earth is too big. In order to detect these millihertz, you really have to go into space to be in a place far away from the Earth. So you might have a chance of detecting very, very low frequency gravitational waves. This is part of the reason you want to go to space to detect millihertz gravitational waves. But let me paraphrase my question. Why we want to detect millihertz gravitational waves, right? We already know there are 100 hertz gravitational waves. Why do we care about the millihertz gravitational waves? Yes.
I guess going back to your previous assessment, that will give you access to 10 to the million solar masses black holes, right? Like the center of
Yes.
galaxies and so on.
Exactly. This is the answer I'm anticipating. Yes. Remember, the frequency actually is proportional to the inverse of mass. So if you can detect the lower and the lower frequency, the black holes you are going to detect will be more and more massive. Okay. So LIGO Virgo is detecting 10 solar mass black holes, around 10 solar mass. And it's operating in the 10 hertz, 100 hertz. Okay. So if you can go down the frequency by 5 orders of magnitude into millihertz, then your black holes will be boosted by 5 orders of magnitude. So you are detecting 10 to the 5, 1 million solar mass black holes, these monster black holes. We know these black holes exist in the center of the Milky Way. There's a 4 million solar mass black hole there. People have been trying to take photos of black holes, and the black hole people have so far taken the photo is a M87, and it has a black hole of a 6 times 10 to the 9 solar mass black hole. So there are these monster black holes out there in the universe. We know they are there.
Are you sure about that, Xian?
Sure about what?
Are they black holes?
Are they black? Okay. Let's say they are very, very compact object with such high density, and currently the most natural model to explain them still seems to be the black hole model. Actually, I personally hope one day maybe we will overthrow everything, this classic idea, and maybe find that they are not black holes. But so far, I call it a black hole with quotation marks just to refer to this concept, okay, or this kind of object, high density, very, very, very large mass of this kind of object. Okay, so there are these monster objects out there, and if they merge, they produce millihertz gravitational wave or even lower frequency gravitational waves. This is why there are this motivation to go into millihertz to see these things. Okay.
I have a question.
Yeah.
Please. Can gravitational waves be filtered? So like a light wave, you can see different frequencies. So can gravitational wave be filtered so we can detect maybe different masses than the real one?
Gravitational waves couple with matter very, very weakly. The only coupling you can imagine is through gravity. Okay, so it's almost it's very hard to affect the gravitational wave. You cannot absorb it. You cannot manipulate. You cannot create gravitational waves using man-made devices, for example. So in this way, it's very, very difficult to filter it by man-made devices, let's say. So in nature, in the universe, are there something screening?
I have a question there, Professor. If you have a binary system, maybe with 2 black holes, maybe there should be interference between the gravitational wave of the black holes. So in that case, how can we say that the gravitational wave is being affected because of that interference?
Can you repeat your question? I'm not sure I quite get your question.
I'm talking about if you have 2 black holes, so they are close. Maybe there should be interference between the two, the gravitational waves, no?
Okay, so you're saying that seems 2 black holes. Okay, then each black hole is producing some gravitational wave, and there is an interfering with each other, right?
Yes.
One black hole actually almost never produce any gravitational waves. In astrophysical conditions, you cannot have one black hole producing gravitational wave if you have already put the black hole there long enough. Okay, because basically it's very stable. to produce a gravitational wave, you have to have some kind of a quadrupole moment. So what is quadrupole? If you have a ball, the ball also only is isotropic. You rotate the ball, it doesn't produce gravitational wave, okay? Because it has monopole. And if you have a disk in this plane, and you rotate your disk along the symmetric axis, you don't have gravitational wave, because disk does not have a quadrupole. If you rotate this way, that does not have a quadrupole either. It's not even a dipole, actually. Is it a dipole? No, it's probably not a dipole. So you really need something very, very asymmetric. Two black holes, for example, each can be imagined like a point orbiting each other, is very, very asymmetric. It's not symmetric compared to a ball or a disk. That's why when two black holes rotate around each other, they produce gravitational wave. So in this way, you really need two black holes. They together form one source, and this source is radiating a gravitational wave. Okay, so it's not one black hole is producing wave, another black hole is producing wave, and the two waves are. It's not like that. The picture is wrong. The two black holes, they together form a single source, and you see waves coming out of this single source.
Okay, thanks.
And what if you have two couples of black holes that they are producing gravitational waves independently, but these gravitational waves they superpose in some place in space? Wouldn't be there an interference?
Yes, gravitational wave is like any other wave. If their waves are close to each other, they will interfere. Okay, and if their phases are, say, if you have two exactly the same sources producing the same frequency wave, and they happen to be the phases happen to be exactly the same, then you have constructive wave. If the phases are different by like pi, then they are destructive. In this sense, gravitational wave will interfere. But the difficulty is, in universe, you almost never have two exactly the same gravitational wave sources. Every star is different from a little bit different from the other star. Every black hole is different from another black hole, and every black hole binary is different from another binary. It can be different by a little bit mass. The mass ratio of the binary, how the two black holes in the binary, how their masses compare, is always a little bit different. Their spin is a bit different. So it's almost never possible to produce exactly the same gravitational wave from two completely different binaries. So interfere does not happen in this case. Okay, you have two sources that are producing wave that can interfere. Almost never happen in the universe. However, there are special cases called gravitational wave lensing. If you have one source in the background, and there's a bigger galaxy in front of you, and your observer is on the other side, okay? Then the middle big galaxy might lens the background gravitational wave source and produce several images. And in some very special conditions, these images, their waves come to the observer around the same time and almost has the same frequency, and these images will start to interfere. Okay. So this is a very interesting phenomenon, a gravitational wave lensing and then interfere. And this is actually what the LIGO-Virgo people have been trying to look for in their data. But in order to have this interfere, you really need a very, very special configuration. The source, the lens, and the observer, it has to be aligned in almost one line. And this condition is very rare. That also explains why even today, LIGO-Virgo didn't detect any such lensing systems yet.
I have a question.
Yes.
Does a black hole radiate all the energy that it absorbs, or it remains a part of it to use it, for example, to increase its size?
Oh, this is a fantastic question. So let's first forget about the black hole and think about if you have an electron here, and there's electromagnetic coming in. Does the electron absorb the energy of electromagnetic wave. This is the exercise you probably did in your college when you were learning electromagnetism, right? Yes, the electron will absorb some of the energy because the electromagnetic wave comes in, it will excite the electron. The electron initially has no energy, but when it's excited, it has energy. Where does the energy come from? It's from the electromagnetic wave. It's absorbing the wave. So on the other hand, it will react on the wave. So the wave passing by and go to further away. These waves actually will be weaker than the waves coming in. So electron is going to absorb the electromagnetic wave. If you replace the electron with a black hole, and you replace the electromagnetic wave with a gravitational wave, very similar things will happen. The black hole actually can absorb some of the energy, which means gravitational wave will put some energy to the black hole. Then the black hole will actually has a little bit more energy. What does the black hole do? It vibrates. Okay, and in this way, when the black hole vibrates, it's no longer a symmetric black hole. Itself is also emitting gravitational wave. So you have a wave coming in, excite the black hole, and then wave going out. This going out wave will contain some energy from the initial wave, but also some energy from the vibrating black hole, because the vibrating black hole is also producing gravitational wave. And this is actually a very interesting phenomenon. And people think, especially the vibration of the black hole and the waves emitted from the vibrating black hole is related to how GR is working, what a black hole really is, for example. If a black hole is not a classic GR black hole, it will vibrate differently and give away different waves. And so this is a very interesting model. But in terms of detecting the wave coming out of this system, it's very difficult because in almost any astrophysical scenario, this black hole is probably already very far away from the gravitational wave source. So when the gravitational wave arrives at this black hole, the gravitational wave is already very, very weak. Okay, and it will excite the black hole, but the excitation is also very, very weak. So when the wave comes out, this wave is almost still more or less the same incoming wave with a little bit of change from the vibrating black hole. But the vibrating black hole, the vibration is so weak that you almost see no change of the outgoing wave. So in real astrophysical scenarios, it's very difficult to detect the wave that is modified by a vibrating black hole.
Okay, thank you.
Mm-hmm.
I have one question. Why it doesn't matter interact with gravitational waves? I mean, not that strongly.
Matter do interact with the gravitational waves. Okay. If you have, say, two lead balls, I choose lead balls because they are already massive, and you have a gravitational wave coming in. Gravitational wave is going to, let me see if it is right. Yes, gravitational wave is going to vibrate these two lead balls, let them oscillate. And you see the oscillation is producing acceleration of the quadrupole moment, right? These are two lead balls, so there is a quadrupole moment. When they start to oscillate, it's the oscillating lead ball is going to produce gravitational waves. Okay, so where does this gravitation? Where does the energy of the induced gravitational come from? Coming from the incoming gravitational wave. So in this way, the lead ball binary system is absorbing gravitational wave and re-emit it. The only problem is that the coupling coefficient is very, very, very low. This is probably tied to the fact that the distortion is proportional to the gravitational wave constant, which is already a very, very small number. And the motion has to be measured in the velocity divided by the speed of light. Okay. Any velocity divided by speed of light, it will be a very, very small number. So a product of these very small numbers, gravitational wave constant, the very small motion, in the end will give you a very, very small induced gravitational wave. In other words, this binary lead ball system is going to absorb gravitational wave incoming, the energy from the incoming gravitational wave. but only a very, very small amount is absorbed. The coupling between this lead ball system and the incoming gravitational wave is very, very weak. In this sense, gravitational wave interact with matter very, very weak. Not like light, actually. If you have two electrons, as electromagnetic wave come in, a lot of energy actually becomes absorbed and scattered in all kind of directions. This is because the coupling between electromagnetic field and the electric charge, for example, is very, very large. Electric forces is a lot of orders of magnitude higher than gravitational forces.
Okay, so
Okay,
I have
thank
one
you.
question.
Yeah.
Yeah, so as we know that when we have binary systems like neutron stars, then we also have the tidal deformations, right? So I'm just curious that how these tidal deformations are related with the gravitational waves, because when you calculate the tidal deformations, there also we have to calculate the quadrupole movements.
The signal is not very stable, but does anybody hear the question? And if you hear it, could you maybe repeat it to me?
He's asking if you can correlate tidal deformations and gravitational waves. So he wants to just know what information you can gain from that.
Yes.
Or if you can gain.
So these are two completely different views. There are different views of looking at what a gravitational wave is. This is probably related to the fact that in GR, you are free to choose your coordinate. If you choose your different coordinate, you might see something different. But in the end, the measurables are the same. For example, I don't want to go to detail, but actually in the early times when people considered the interaction of gravitational wave with matter, they think of gravitational wave as kind of a tidal field. For example, the famous Weber, who designed the Weber bar to try to detect a gravitational wave, but people think he didn't detect anything. When Weber was considering the interaction between the gravitational wave and his Weber bar, he was thinking of gravitational wave as kind of a tidal force propagating in space-time. And this tidal force is going to act on his bar, Weber bar, and squeeze and stretch his Weber bar. This is why the Weber bar gets vibrated, and you can detect its interaction with the gravitational wave. In this way, you detect a gravitational wave. Okay. So in the early times, people are thinking of gravitational wave as a propagation of tidal forces. This idea, although it's still true, but it's very difficult to calculate if you want to calculate the response of a laser interferometer to the gravitational wave. Well, there are much easier ways to calculate the response of say 4 kilometer laser interferometer to the gravitational wave. And in that method, you basically throw away the idea of a tidal field and think of gravitational wave as just changing the metric. Okay, the coordinate of the two ends of the arm does not change, but it is a metric between them that is changing. It is a much simpler way to calculate the response of interferometer. So maybe that's part of the reason today we hear a lot of this TT gauge or like a metric is perturbed, and we hear less and less the propagation of tidal field. But both scenarios are valid, and if you do the calculations seriously, they will lead you to the same results.
Okay, thank you.
I have a question. Is there a chance that some movement, let's say you have a neutron star that's moving away from Earth, from LIGO detector, and that somehow we can be seeing a frequency that has been modulated by Doppler effect?
Yes, of course. So I guess what they are saying is the neutron star is leaving the Earth, right, or passing by the Earth, it produces a gravity on the Earth that is changing with time. And anything on the Earth, like electromagnetic signals or gravitational wave we try to detect on the Earth, will also be affected by this gravity, time-varying gravity. And this time-varying gravity induces effectively a shift of the frequency. Is that what you are trying to say?
Yes, but I was thinking primarily on a relative movement. Of course, this is not a classical thing. I mean, it's not a classical sound Doppler effect, right? But at some point, I think that maybe a relative movement can produce that the space-time that we the space-time configuration that we can see in Earth can be modulated or can be changed by Doppler effect.
And this is actually what my student, actually Paul is also a co-supervisor, Alejandro. I'm not sure if Alejandro is here. It's actually Alejandro's PhD thesis. So they're basically saying if gravitational wave sources are moving relative to us, okay, of course we see the gravitational waves get a Doppler blue shifted or red shifted depending on the direction of the motion. But other than that, do we see other signatures that we can use to tell this gravitational wave source is moving, and this gravitational wave source is moving with a relatively small velocity, because in the end everything in the universe is moving relative to us. So gravitational wave sources should also be moving relative to us. Okay, I probably don't want to go into the details of what Alejandro has got, and because Alejandro is also going to give a talk later. And I don't have a good way of explaining his results in a couple of words. This is something worth looking into. And so far, maybe when the gravitational wave source start to move, you see the radiation pattern, like how much energy is radiated this way, how much energy is radiated in that way, is going to change. Okay, this is for sure. And but as an observer, you don't see the global radiation pattern of the source. Gravitational wave source is always very far. Your observer is a very small dot far away from the source, right? Almost doesn't change. So you only sample a very, very small region in the wavefront. So you only sample a very small part of the information. Is that part of the information enough to tell you that the source is moving or not? So far, we think the information we have got is too weak. In other words, signal to noise ratio is too low for us to tell the difference. But this is something actually has no obvious answer and is worth looking into.
Thank you.
Professor, I had a question.
Yes.
So, do gravitational waves have a permanent effect on matter? Like, if a gravitational wave passes by a matter, does it permanently displace it or anything that sort?
Sorry again, I didn't quite understand the question. Anybody can maybe paraphrase the question for me? Thanks.
He's asking if gravitational waves have any fundamental effect on matter. So
Yes.
Like, does it have a permanent effect on matter? Like, if a gravity wave passes by matter, does it permanently displace it?
Yeah. Okay. Yes. There's a effect which I don't fully understand yet, but you do see people discuss it in the literature, and I think it makes sense to me. That is, if you have a burst of gravitational wave and it passes, okay, the space-time before the gravitational wave arrives and the space-time after the gravitational wave has passed are not the same. There's a residual effect, sort of. This is a space-time before the wave comes, and this is space-time after the gravitational wave has passed. Okay, so there's a residue, and this residue is going to produce some detectable effect, such as the time travel, the travel time in the arm of an interferometer has changed permanently, for example. So try to answer your question. Gravitational wave not only do affect matters, it even affects space-time permanently, according to the theory of the people. But I have to say, I haven't fully understood the underlying equations and mathematics of this theory yet.
Are there any keywords I can search to learn more about this?
Look for gravitational wave memory effect.
Memory effect.
Memory
Okay.
effect.
Thank you.
Yeah.
And I had one more question.
Yes, please.
Yeah. So, how do we plan to take care of like asteroids coming and hitting Lisa in space? Like even if we have a slight inch of the disturbance, uh, it can destroy. I mean, totally destroy the precision, right? So.
Yeah. Very, very good question. This is actually a very nice exercise to do, especially when you study, say, dynamics in astronomy. It's a probability. Although there are asteroids in the solar system, but they are not. In order for them to hit a detector like LISA, each LISA detector probably is going to be a couple of meters in diameter. Okay, in order for one asteroid to hit a target which is over the size of 1 meter, and you can calculate the probability given the number of asteroids or the density, mean density of asteroids we know in the solar system and their velocities. Okay, you can use the so-called keyword is gravitational focusing effect to try to calculate the probability that they are colliding into each other. You will see that the probability is extremely low. Okay, so in order for this one event to happen, I'm pretty sure you probably have to wait longer than the age of the universe, probably, for sizable asteroids to hit the LISA satellite. Okay, but we know there are a lot of the space debris, much smaller than asteroids, and there may be more numerous. So it probably poses a more dangerous situation to the LISA mission.
Okay, thank you.
I have a question.
Okay, sorry.
No, please go ahead.
No, it's okay. You can go ahead.
Okay. So it was from a point that you made at the beginning. So if two main sequence stars orbiting each other produce gravitational waves of very less frequency, and compact objects such as neutron stars orbiting each other produce gravitational waves of kilohertz frequency, then the black holes they fall in between, right? So how do you say that the frequency of gravitational waves produced by the merger of two black holes is the upper limit?
Oh, this is a combination of the mass and their sizes. Okay, so I probably focusing too much on the size, but don't forget mass also plays a role in this game. I was comparing two 1 solar mass neutron stars, their top frequency, to two 10 solar mass black holes. Okay, this is not a fair comparison. Okay, if you have to do a fair comparison, you probably want to think of say 1 solar mass neutron star, 1 solar mass neutron stars and two 1 solar mass black holes. Okay, and if you do that exercise, you will see, yes, black hole mergers with 1 solar mass black holes each are producing even higher frequencies. But these 1 solar mass black holes are not the astrophysical black holes we know. Stellar evolution in the end will produce black holes almost always higher than 3 solar mass to 10 solar mass. Okay, so in normal astrophysical environment, you almost never have 1 solar mass black holes. 1 solar mass black hole might form in the early universe, at the beginning of the universe, and they are called primordial black holes due to fluctuation. But these are very hypothetical, and so far there's still no strong evidence for the existence of a primordial black hole. So that's what I intentionally ignored at the beginning. But if you want to do a fair comparison, you can compare 1 solar mass neutron star mergers with 1 solar mass black hole mergers, and it will answer your question. In the end, 1 solar mass black hole mergers produces higher frequencies in the end.
Oh, thank you.
Okay.
No, you go first.
Okay, thanks. So my question is a bit not directly, probably maybe related, but I'm more curious. So with LISA, you expect to see supermassive black holes, right?
We expect to see supermassive black holes, yes.
But I had recently seen, or maybe you can correct me if I'm wrong, about some galaxies which might have two supermassive black holes, which was very confusing because it goes against on what I have been consuming so far in literature, that you have one galaxy will have one supermassive black hole, and here we are talking about two.
First of all, let me first say, LISA detect a supermassive black hole, but the main target of LISA is already binary supermassive black holes, two supermassive black holes that are merging, that will produce millihertz gravitational waves in the LISA band. Okay, this is already the main target of LISA. So we are already talking about two supermassive black holes merging into each other.
But this is effectively then saying that you are also trying to see, this can also, actually this is more for me a conceptual question. So when you talk about two supermassive black hole mergers, does it also imply that this might be also two galaxy mergers? Or is it happening within the same galaxy? Because
exactly, it goes along the line you are thinking. So the question is, how come two supermassive black holes can get so close and they merge, right?
Right. And so also, yeah, sorry, please go on.
Yeah, so we have some basic astronomy observational facts. One fact is that a lot of sizable galaxies, like our Milky Way or even larger galaxies, M31 or some elliptical galaxies, contain supermassive black holes in them. A lot of nearby galaxies do have supermassive black holes in them. This is factor one, okay? Fact two is we see black holes merging, especially bigger galaxies merge probably more frequently. These are two observational facts. We already see that in the universe. So if you combine them, galaxies have black holes in them and galaxies merge. You will naturally yes. But it's not difficult for you to start to think, right? Start to think, maybe black holes, after the galaxies merge, black holes may also be brought to the same center and merge, okay? So it's not difficult to think.
Do you see galaxies?
But then
do you see galaxies emerging in the universe?
We see, yes. I know somebody will have strong objections to what I just said.
You're cheating here. You don't see galaxies merging. You see galaxies interacting.
We see galaxies interacting, and we also see some galaxies actually, interestingly, with two cores.
Yes, that's exactly what I wanted to point towards, because I wanted to ask whether in such cases, is it a scenario where we might expect a merger and it hasn't happened, or will, because I cannot appreciate the mathematics here, so maybe I'm completely wrong.
Let's say there are people believe that yes, after galaxies merge, black holes do. There are mechanisms to bring black holes into a very small region and merge. There are people believing that, so they produce gravitational waves. There are also people don't believe in this. They say it's too difficult. There are probably this whole process will be hindered by some other unknown processes or known processes they think will actually happen in the universe. But the bottom line is LISA will try to answer this question, right? If LISA detected binary supermassive black hole mergers, then black holes should merge after galaxies merge. If LISA don't see anything, then supermassive black holes binaries do not merge, do not even form after galaxies merge. So LISA actually is in a good position to finally answer this theoretical question.
All right, thank you.
Okay, so I have a different kind of question. Can gravitational waves of black hole mergers, for example, or cosmic gravitational waves, can tell us anything about the about topological defects or the topology of space? And can LISA detect such topological defects?
I think potentially yes, but how is still something we have to figure out. I say potentially yes, is because when we have LISA, then we can detect the black holes up to, say, a redshift of 10, 20. Okay, there's no object, astrophysical object so far we have detected at a redshift of 10 and 20 using classical electromagnetic waves. Okay, gravitational waves actually opens this new possibility of detecting objects from that early universe. If there are some topological, say, defects in the universe, then they will be affecting the propagation of gravitational wave. And in other words, gravitational wave will feel those defects. And by analyzing the gravitational wave we received today, maybe there's a chance of finally digging out the defects. So there's its potential. How we can do that is another different question, because maybe there's an effect there, but this effect is degenerate with some other, say, much common or astrophysical phenomena. For example, if there are, say, black holes do not merge in vacuum, there are gas or stars around it, and the existence of this extra matter actually changes the waveform. Okay, and this waveform looks like a defect of space-time at the early universe. How can you distinguish these two completely different scenarios? One is a normal astrophysical scenario with some matter around the black hole mergers. The other is a fundamental, a new phenomena related to what is really space-time, right? But the observable that these two models produce are exactly the same. It's a distorted waveform. Can you tell the difference? It's still an open question. Or what difference, what signature you want to look for to tell the difference. Okay, this is actually is going to be a very hot topic in the research, I believe.
Oh, okay, thank you.
I have a question there. Is there a chance? I have asked this question a couple times, but I haven't understood the answer yet, and I really will appreciate your income on it. Is there a chance that space-time configures everything? What we know as standard model particles are really space-time configurations, so or space-time and something else. I mean, is there a chance that through general relativity, we can describe magnetic fields and electric fields and what we know as mass? Is there a chance that is a property of space-time?
I don't think I will clarify that either. But what I think is that GR is basically describing the macroscopic feature of a space-time. Okay, but when you want to say what a matter is, what elementary particle is, it's quantum mechanics, it's quantum physics. So in order to understand if quantum mechanics actually is compatible with GR, this is actually what you are really asking. And then maybe a related question, is gravitational wave going to help us finding the relationship between quantum mechanics and the GR? I think yes. I think it's very likely. Because let's take black hole, for example. You probably have heard of this black hole information lost paradox. Why information could be lost? Are there solutions to that? The solution actually always has something to do with the quantum mechanics and the GR describing the black hole. Okay, and these combined theories, although very ugly today, are always predicting the black hole is not the classic black hole. It's not a classic GR black hole. It's always some new feature in it, and the feature actually will be manifested when two black holes merge. Okay, you will see it in the gravitational waves. The only thing is that the feature could be very prominent if our model is like this, and the feature could be extremely weak if the model to combine GR and quantum mechanics is constructed in another way. So there are theoretical uncertainties, but they actually predict in principle that yes, in gravitational wave, when two black holes merge, there is some new feature in it. If we have very high signal to noise ratio, we have a higher chance of finally seeing such a feature. What kind of observation is going to produce superb signal to noise ratios? LIGO work today detecting binary black hole mergers, and the typical signal to noise ratio is around 10. LISA in the future will detect supermassive black hole binary mergers, like we have said a couple minutes ago. And the signal to noise ratio we are expecting is around 100, if not 1,000. Okay. So in this sense, LISA is also in a much better position of maybe finally resolving the black hole information loss paradox, and then maybe find a clue to combine quantum mechanics and general relativity. So in this sense, I say yes. There's a way by studying gravity.
Because, for example, a couple days ago, I think it was yesterday, we have a lecture on numerical relativity. And in this lecture, the professor, he described that particle points in Newtonian physics are the equivalent to black holes in GR. So the question is, because it's hard for me to picture that there is something else apart from space-time. Because if we describe a planet in space-time, we will describe it as a particle, as a point particle on a wave, right? So we're doing the same over and over. So my question is, because for me it's hard to understand. For me it's easier to understand that space-time is everywhere than it is not everywhere. I understand that this is a very typical question on quantum mechanics relation with the GR, but at some point, I guess it's normal for me hard to picture that there is something apart from space-time.
Don't worry, nobody understands it. If somebody understands it, then this person will already get a Nobel Prize for it. So I think this is because maybe today, if you look at the theories in physics, there's still no theory that is good enough to explain, to have a unified explanation to quantum theory and the gravity. Okay, and to reach that day that we have a unified theory, I think we probably have to invent some completely new or think out of the box. So if you don't understand, don't worry. But that shouldn't prevent you from inventing your own theory of unifying it.
Thank you so much.
People, do you have more questions for Xian?
Yes, I have a question. What do you mean by a black hole shows new features? What exactly are these features here, and how is that found in gravitational waves?
For that, I have to confess that I only can recite what I have seen in the literature, and that doesn't mean anything that I understand it. Okay, so what I see in the literature, that if the black hole, say, is the quantum black hole, then there must be some very funny things happening at the event horizon. What that effectively produce is a kind of a potential that is deviate from classic GR potential of a black hole. For example, in GR we have only one boundary, which is called we don't have to fully understand, but there's a boundary called a photon ring. Everything, even photon falls into the photon ring, doesn't come back. But if it's a quantum gravity, besides the photon ring, further inside there's another kind of potential barrier produced by some quantum effect. So photons falling into the photon ring will hit this barrier and will be reflected back. This reflection actually creates some new feature, for example, in the gravitational wave you see. So by this kind of ideas, people have actually predicted that there might be some signature in the gravitational wave that you can use to probe if there's anything funny happening at the event horizon.
Okay, thank you.
Xian, how do we know that two black holes merged? Is it when their event horizons touch, or how do we define that?
Well, first there's numerical relativity, and there are real observation. Like you see a wave, and how do you tell the two black holes already merged, right? So in numerical relativity, there are ways to define when the event, you can look for the event horizon, so to say. And after a very late stage, you see only one event horizon, and you know the two black holes completely merged in your computer simulation. Okay. In the observation, what you see is a waveform, but this waveform, you observed waveform, fits the numerical waveform so well that it's very hard for those numerical relativity people to believe that black holes are merging otherwise. So there's only one reasonable interpretation that the black holes that is producing with waveform has already merged.
I guess the question was more in the sense of at some point there's no more signature, there's no more gravitational waves produced. This is because the thing had a quadruple and eventually becomes only one. But I'm since black interiors are unknown and it is not very clear, I suppose, like how close do the two boundaries have to get together for us to consider this is
yeah. To me it's distance, like how close the two black holes should be in order for the event horizon to touch, right? There's the astronomers' approach. Like my approach is okay, when the two black holes are separated by the Schwarzschild radius, they must have almost already merged. Okay, but in GR, distance is a very tricky idea. Okay, if you well, now you have heard Leo's talk, maybe last year. How to define the center of black hole is already very problematic. How can you define the distance between the centers of two black holes? Okay, so. So there are probably more stricter ways of think of how you define the separation of two black holes. But it must be in a fully relativistic way that I cannot easily interpret at this point. Yes.
So I have a rather naive and maybe a bit provocative question. I was just wondering, if I remember correctly, the LISA Pathfinder results were like extremely nice and good. So I was just wondering, why do we need like 15 years to launch LISA?
Xian, maybe you could make a summary of what the LISA Pathfinder is before.
Okay, LISA Pathfinder is a test. Is also a small interferometer in one satellite. Instead of 3 satellites, put everything very compact one into one. So to test some key features, can you do interferometer in space? Can you basically this very key technology of zero dragging sort of technology, and can you monitor the position very, very well? Remember, we have to measure the distance distortion of 10 picometer. Can we really measure a displacement of that small distance? So LISA Pathfinder is aimed at that. But it's also much simpler than what LISA really is, I think. For example, you do interferometer in one satellite, you don't have to worry about you lose your photons when you do interferometry. When your satellite is separated by 3 million kilometers, even if you shoot a very powerful laser from the starting point, at the end point you receive maybe only 1 or 2 photons. Okay, how can you receive these photons and in particular register the phase very, very accurately, so you can send another beam of laser back to the other satellite, so that the light makes a round trip to measure the distance. So these are some of the differences that you are going to experience or you are going to see between the real Lisa and the Lisa Pathfinder, and this is these kind of differences that is making Lisa so difficult.
Okay, I see. I understand.
I have a question. Is there how do you describe the coupling in LIGO mirrors with gravitational waves? As far as I know, the interferometer works just like Michelson Morley. Is that how you spell in English? And so how do you describe the interaction between the gravitational wave and a mirror in a LIGO experiment?
It's it's probably last question because it's already 12 here. It's probably better to first understand what's going on in one arm, right? You send the light from here to here, and the light makes a round trip. You look at how much time it takes. You measure the distance. Okay, this is a much simpler example to understand the basic ideas. When gravitational wave passes, okay, it effectively changes the distance of this, the length of this arm. The two ends of the arm actually get stretched or squeezed depending on the phase of the gravitational wave. So when light makes round trip, by the way, light makes round trip very fast. Okay, so because arm is not very long compared to the wavelength of the gravitational wave, arm is very, very short. So you can almost think when gravitational wave is at this phase, the light already makes round trip. Because gravitational wave changes the distance, so you see the round trip time is different. This is how you measure really the whether or not there's a gravitational wave.
Yeah,
So
but about the fact that the gravitational wave is interacting with the particles in the mirror. That's what I was pretending to ask.
So you're worried that the mirror also gets squeezed, and so its shape will change, right? And that is going to affect the measure of the distance. That's of course is happening, but don't forget, the mirror is held together by electromagnetic forces. Electromagnetic force is much stronger than the tidal force brought in by gravitational waves. So the mirror actually hold it together very, very well. Mirror is very rigid. The gravitational wave passing by the mirror is not going to change the shape of the mirror very much. Almost doesn't change. For the purpose of measurement, the change of the mirror's shape doesn't affect your measurement.
Just would have to care about quantum noise.
Quantum noise.
Okay, so Xian is complaining because it's 6:30. Sorry, 12:30.
No, I don't want to delay the next speaker's talk.
I mean, it's also 12:30 in Cuba. But yes, we have had a lot of questions, and this is why I actually prefer the talks to not have slides. And I've been told by Soldan, who was here, that he's not going to have the slides either. So I suggest, Yorgo, that we stop now the recording